Hello everybody, I'm Mattia Cerrato. Today I will be presenting to you Fair Pairwise Learning to Rank, which is joint work with my colleagues at the University of Mainz, Marius Köppel, Alexander Segner and Stefan Kramer, and with my PhD advisor from the University of Torino, Professor Roberto Esposito. So perhaps you've heard about neural networks, and neural network models are being increasingly used in learning to rank tasks and information retrieval in general. The issue with those models is that they're inherently opaque, meaning that they have very big parameter spaces, and this prevents us from understanding exactly why they're taking the decisions that they are taking. So when we are dealing with training data which contains sensitive information such as race, ethnicity or gender, then we have very little guarantees about their fairness. When we talk about fairness in machine learning, we are referring to the situation where our training data contains biases against a specific group of people. If that's the case, then those biases can also be learned by the machine learning model. So there are a number of possible definitions and scenarios in fairness in machine learning, and we will be talking about disparate impact when we observe that our model is giving positive outcomes with different rates to people that belong to different groups. So to understand this more easily, perhaps the best running example might be a model that is assigning loans, but those loans are assigned with different rates to white and black people or to men and women, for instance. And this is the disparate impact situation. When we refer to disparate treatment instead, we are talking about the situation where the model is taking different decisions for individuals that belong to different groups, but that are otherwise similar in their features. Lastly, in disparate mistreatment, we refer to the situation where our model is displaying different error rates for different groups. So our approach to avoid those situations is building on a fast pairwise ranking model, which is called the direct ranker, which has been developed by Marius Köppel, Alexander Segner and Professor Stefan Kramer among the others, and we will be employing a couple different strategies so to encourage fair rankings. We will be employing the gradient reversal layer by Jaroslav Ganin and others, and we will be employing the noise module, which I've developed alongside Professor Roberto Esposito and Laura Lipuma. So by employing those layers and modules, we will be introducing a family of neural architectures that are able to rank without discriminating. So just a few words about our base model, the direct ranker. The direct ranker takes its name by the fact that what it does is comparing two documents, document 1 and document 2, by extracting features from those documents via those two layers and those two networks N1 and N2, which actually have shared parameters. The feature extracted are then subtracted, and there is output neuron here. So this output neuron, if its activation is positive, then document 1 will be more relevant, and document 2, if the activation is negative, then document 2 will be the more relevant. And the name refers to the fact that it's really just directly comparing two documents. So it is possible to show that this model is going to learn a total quasi-order by construction, and I will not be referring to the details here. If you're really interested, I encourage you to read the original paper by Marius, Alexander and Professor Kramer. So what we are doing in our fair direct ranker framework is to employ a multi-objective loss with the common ranking term here and the biasing term here. We also will have this hyperparameter gamma, which you can pick and choose. Usually you do so via hyperparameter tuning, any kind of hyperparameter tuning you want to do. And by minimizing this loss, you will obtain a model that is able to both output relevant outputs because of this term, but also fair outputs because of this term. And just a very little bit of notation here, delta y is the difference between relevance classes in the two documents. X1 and X2 is the representation, the feature that we have for our two individuals or documents, and S1 and S2 refer to the sensitive attribute that we care about for those individuals. So perhaps race, ethnicity or gender, sexual orientation, any kind of information that you care about and you do not want to discriminate for. Okay, so the first model that I'm going to show you is the FAIR adversarial direct ranker. And what we do here is we've added to the base direct ranker model those two subnetworks which do not share parameters actually, NN1 bias and NN2 bias. And what those two subnetworks try to do is they classify the sensitive attribute for document 1 and document 2 respectively. We will be having a loss term, two loss terms actually for those two documents, and we will be having some gradients for NN1 bias and NN2 bias. And what we do, which is relevant here to obtain fair representations, is that when we backpropagate the information in NN1 and NN2, we are going to revert that gradient information. We're going to negate it. So this has been studied extensively in both fairness settings and in domain adaptation settings, and what it is doing is that we will be obtaining features which do not contain any information about the sensitive attribute, if trained properly, obviously. And obviously having features which do not contain information about race, gender, ethnicity, or any kind of sensitive attribute is very desirable for fairness. And again, we have two debiasing networks, and the gradient information for those debiasing networks is inverted when we backpropagate into the main feature extraction networks. Those are the loss terms for the model. Here the ranking term is quite basic. We're just taking the difference in relevance classes. We're subtracting the activation that our output neuron has displayed, and we square that. And for the biasing term, here we are just showing the cross entropy loss when you have just two possible values for your sensitive attribute, but that is not a requirement. You can also have any kind of sensitive attribute, even with more possible values. Sorry. The second model that I would like to show you is the FAIR flipped direct ranker, and here what we do is we've added a single debiasing neuron, so to speak, to the base direct ranker model. So what this debiasing neuron is trying to do is trying to rank the two documents, the two individuals, based on their sensitive attribute. The trick here is, once again, to revert the gradient information when we backpropagate into the feature extraction networks. And what we are trying to do here is encouraging the network to see that there is no reasonable ranking between sensitive attributes. And again, this is very relevant for fairness applications. So once again, the features extracted from domain networks are ranked and according to the sensitive attribute, but the gradient information will be flipped. And here is the full loss for this kind of model. The ranking term hasn't really changed, and the biasing term is very similar to the ranking term. Here we have the difference between the values in sensitive attributes, and we are subtracting to that the value for our the biasing neuron, and we are squaring that. Again, we have this hyperparameter to regulate between how much we care about rankings or fairness, relevance and fairness rather, sorry. Okay, but it is also possible to combine those two approaches, so you can add both the biasing networks and the biasing neuron. So what you will get is this kind of loss term. The figure would be a little busy, so I'm not going to show you that. And this is just concatenating the loss term, the fairness loss term rather, for the FAIR flipped direct ranker, and the loss term for the FAIR adversarial direct ranker. Okay, another thing that we've experimented with is the noise module, and the assumption here is that we have this neural activation here at layer I for neuron K, so this is just the activation of a single neuron somewhere in the network, and we are worried that this activation here is very much correlated with the sensitive attribute, so it is very important to suppress it. So if we want to do so, with the noise module is actually very easy to do when compared to, for example, with a fully connected layer. So what you would do in that situation is that you will set this weight here, W1, just to a very low value to suppress the activation. And another thing that you can do is that you can regulate the amount of noise that you're going to mix with the activation to make it, how would you say that, unreliable. And by setting up this value here, W2. And here this is the full equation for the noise module. Okay, so as far as the experimental setting is concerned, we've experimented with 4 different datasets, and I do not think I have enough time to really go into that in depth, but I will just tell you that the COMPASS dataset has the sensitive attribute. We have whether people are black or white, and the ground truth here is just the relevance class. And the law students dataset has both race, ethnicity as a sensitive attribute or gender, so we have 2 different datasets here. The adult dataset is for credit ratings, and the sensitive attribute will be gender. And Wikitalk is about comments which are taught as toxic in the Wikipedia talk pages, and the sensitive attribute is whether a problematic word is appearing in the comment or not. As far as models are concerned, we're going to use a baseline unfair ranker, so you can think about it as the fair adversarial direct ranker maybe, but with gamma set up to 0. We're going to use the DLTR model by Zelicke and others, which is sort of a fair approach to ranking that is, however, based on the ListNet model. We are going to use all our models, so adversarial, fair flipped, and adversarial, fair flipped. And we will be showing experiments that include or do not include also a noise module as the very first layer in our network. Okay, so to evaluate our models, we're going to use the NDCG at 500 as to evaluate the relevance of the rankings. And to evaluate the fairness, we're going to use the disparate impact and disparate mistreatment settings. So for disparate impact, we're going to use the normalized discounted difference, and this metric is going to tell us at different points in the ranking what is the difference between the proportion of protected individuals, so maybe women or black individuals, in the top I documents, and that is going to be compared with the proportion of protected individuals in the overall populational query. So obviously values close to 0 are desirable, and this metric is really taking into account the disparate impact setting. To evaluate disparate mistreatment, instead, we're going to use the group-dependent pairwise accuracy. So you're going to have a set of groups, G1, GK, and you're going to evaluate this metric here, which is the group-dependent pairwise accuracy. So this refers to the ranking accuracy on documents which are labeled more relevant and belong to group I, and the ranker accuracy on documents which are labeled less relevant and belong to group J. So this difference here should be close to 0 if we want to avoid disparate mistreatment. And I'm just going to go into the results for a single dataset. And what we see here is that this line down here is the state of the art without taking our models into account, and this line, the dotted line on the top, the grayish dotted line, is how much we've pushed the state of the art by also employing our models. And here we see that the adversarial fair direct ranker, which also employs a noise module, is really obtaining rankings which are very much fairer than the baseline, but a little bit less relevant, which makes sense. And when we evaluate instead based on GPA, we see a kind of similar situation when it is instead the adversarial fair flip direct ranker which is doing very, very well. And what we've seen that was quite interesting is that we've also experimented with the fair ListNet, the LTR, with a noise module, and we've seen that that model is also really made a little bit more fair when you also include the noise module, which was interesting and unexpected. So the takeaways from this is that when compared to other models, our framework is able to learn fair and relevant rankings while taking into account different evaluation metrics, so both in disparate impact and disparate mistreatment settings. Also, if you use the noise module, as I was just telling you before, with other ranking models such as this fair ListNet, the DLTR, this can also be beneficial in terms of fairness. So I'd like to thank you for your attention, and if you wish to do so, you can find in the description section here on YouTube the link to our experiments and the links to our code base. And once again, thank you very much for your attention.